Hello and welcome back to Calculus 1. After a million years, I guess. So, today on the menu, we have word problems, right? These are derivatives as rate of change. We are going to use derivatives to measure, understand physics, business, economics, and that kind of stuff, which is awesome, in my never humble opinion. So we begin with discussing the first topic that was discussed when Newton invented this, and that is the topic of velocity, acceleration, position, and the rest. So, in order for me to go from point A to point B, I have to move through space. Now, as you can see, relatively to that point and relative to you, I am not moving. So my current speed, velocity, is 0 in respect to the point where I want to go in respect to you. And in order to get where I want to be, to cover the distance that I want to cover, I have to change my zero velocity into a non-zero velocity so that I can change the position. So we have in physics name for every single one of these concepts. Change in velocity is called acceleration. You know that because I hope you stop for red lights, stop signs, right? So your speed at that point is 0. And then you have to accelerate, meaning you have to press your accelerator pedal, which is gas. It's the one on the right. I know you've all been behind someone who just doesn't know where that, right on a highway, they don't know where that pedal is. This is the one to the right, just in case that you're one of those people. And no, I will run you over. So you push the acceleration pedal to change the velocity, the speed, from 0 to some number, and that causes you to change the location, the position, from A to B, right? And now you covered the distance in time. All of this, as I mentioned, happens in time. You go this way, and 1 second passes. Then you go back, 1 second passed. So I covered 6 feet in 2 seconds, about 3 feet per second. So we can measure how far you go in a direction you want to go and in what time. And when you write it as a ratio, it becomes the velocity, which is the first derivative of the position function. Position function? Hey, look at the sin x in time. Right? Isn't that sin x? Whee! Right? Throughout the classroom. I have to take parabolic turn to leave the classroom, right? Start over here and then bend, and then bend a lot and get out. You can observe, we can do the experiment. Look at this. Don't worry, I'm a professional. Look at that. It's called parabolic motion, right? So now we have position function, which measures how far you are away from the point of origin, which is from your starting point. Position function is denoted by S of t. It's clearly going to be an S because word position has an S in it. So it's position function. The other ones are velocity function. Now that one is v of t. It would be better if it was L of t. You always pick a third letter, but acceleration function a of t. All of these functions are measured in respect to time. And you experience them all while driving. There's another one that I'm going to add. It's not in your book. We will cover it in physics, and there's more after that as well. Let's put jerk, which is j of t in this case. The reason why I want to add this one is you experience this every time when you slam on your gas or your brakes. Both gas pedal and brake pedal are both acceleration pedals. One accelerates, makes you go faster. The other one decelerates, makes you go slower. So one is positive acceleration, the other one is negative acceleration. Both of those pedals that you are using are acceleration. Oh, by the way, if your car has a third pedal, it's time to upgrade, okay? Then don't tell me that you're an excellent driver. You're just inefficient. So now, we have these four. You experience jerk, which means forward or back in a seat, depending on like which one you slam on. Your seat belt is there because of that one. So each one of these, except the first one on top, is going to be a rate of change of the one before. Velocity is rate of change of position in time. And we do that as a derivative ds dt. Clearly, this is what's important, ds dt. Your position is measured in miles. The time to cover it is in hours, miles per hour. It's a rate, miles per hour. So if you are driving 60 miles per hour, you will cover 60 miles in 1 hour. If you are driving 60 miles per hour, but you drive 30 minutes only, you will cover 30 miles, right? Because 60 miles per hour means you are covering mile per minute. I'm not sure if you know this, but most of the highways follow a pattern in the United States, and they try to follow the pattern. All of the odd highways should be south-north, north-south. So 287, north-south. And then 78, east-west, or 80, east-west, right? And then it should be a mile for each exit, which is why some exits are skipped. If you're using 78, you know that Clinton has 15, and then there's 17, also Clinton. And then you have 18, Annandale. And then there is nothing until 20, there's 19. And then from 20, you go to 24, and then from 24 to 26, which is where we are. So not every exit is listed because the exits follow the mile markers. And the mile markers is simply where the state line begins. Your 78 begins in state of New Jersey. That's a mile 0. And then you simply measure a mile and you put the mile marker 1. Right? So those green numbers on the side of the road are the mile markers. If you need to report something as you drive, you are supposed to read off mile marker as you are reporting whatever. So now you can use that knowledge and the knowledge that if you're driving approximately 60 miles per hour to approximate when you're going to get to a place. Because if you know that, let's say you're traveling from exit 15 to exit 26, well, 15 and 26 are 11 miles apart. If you're driving 60 miles per hour, well, that's a mile per minute, 11 miles, 11 minutes. If you're driving faster than 60 miles per hour, well, it's going to be less than 11 minutes. Now, can I do it in half time? Yes, you can, but you have to double your speed, right? That means that you can make it from exit 15 to exit 26 in 5.5 minutes, but you have to drive constantly 120 miles per hour. Which is why speeding doesn't really pay on short distances, right? If you're traveling 300 miles, yeah, you might save 15 minutes if you are willing to risk 3 hours, 4 hours, right, at a high speed. But on a short distance, or on a speed limit 35, and you are, I'm going to do 50. Well, you are going to literally shave off seconds of your travel time, but if you get pulled over, yeah, so don't. Or they ask for license. Anyway, so now your acceleration is a change of velocity. Remember what I said, that when you are at a parking lot or a red light or a stop sign, right? Your car has 0 velocity. In order to change velocity, you have to use a rate of change of velocity, which is called acceleration. So acceleration is going to be the derivative of velocity in time, and that's your gas pedal. So you press the gas pedal, and you see the velocity rise from 0 to 10, 20, 30, 40, right, depending on how much you can get on your vehicle. Jerk is going to be change of acceleration in time. Note that every time when I say the word change, I'm writing a D, because that's what D stands for. It's the change in acceleration over change in time. That's the derivative. It's a rate. And again, jerk, that's going to be of how fast you press your gas pedal or a brake pedal. You don't experience it if you press them slowly, either one of them, right? However, if you're going very fast and you have to stop abruptly, you slam on a brake, right, and you immediately feel it. So the change in acceleration is how fast, how strongly you hit those pedals, either one, because the acceleration one will push you back into the seat. For trucks, it's very, very important and very dangerous to do those kind of things, because they have the cargo in the, I shouldn't call it truck go, in the back, right? And it shifts, right? So if it's not tied down or anything, right, you take off with the, that's why I think it's a very bad idea for Tesla to actually push that big truck they made, right? Because if they put the Model S acceleration in that thing, and then they have a driver who's an enthusiast, right? Presses little and say, okay, oh, look at this, ecologically small, great, right? Everything from, right? The 10 cars after it's like everything is done. So it is each one of these, and now I'm going to move this one, is going to be the derivative of the previous one. Now, if you are trying to understand motion, you will say, when I press my acceleration pedal, I will change my velocity from 0 to some number, which would in fact change my position from where I was to where I am going to. And that's the way it goes. So it starts with acceleration. Well, it starts with how fast you push on these, but we can ignore that. So you press the gas pedal, that causes velocity to change from 0 to 30, and 0 to 30 miles per hour gets you to move the, whatever distance forward. So now we did the experiment. Time for exercise. So, experiment is to observe the path of the object. It doesn't matter what you throw, right? If the object is not self-propelled, it will follow parabolic motion. So whether I throw a bottle, if I throw this, if I throw you, everything will have this parabolic path. Doesn't work for chicken, because the chicken is going to, right? Is going to alter that. Rocket, again, doesn't work, right? Because it has self-propelled component to itself. But if you throw something, you are going to see parabolic motion. The distance in time. The formula which you memorized in physics is that the distance in time, we call this s of t, but in physics y of t, the height at which the object that you threw is given as negative 1/2 gt squared plus v0t plus y0. So this is the standard physics equation, and it governs motion. Now you have these letters. G is what? Gravity, exactly. Not buoyancy, it's gravity. Gravity, 9.81 meters per second squared. So, gravity of 9.81 meters per second squared, or 32.2 feet per second squared. You will clearly know which system of units you are using when you see in your problem 4.9 or 16.1, because that's half of these numbers. So if you see 4.9 and no units given, it's meters per second squared. If you see 16.1, half of 32, right, you have this half, it's going to be in feet per second squared. V0 initial velocity and y0 initial height. Why do you want tall basketball players? Because y0. That hoop is high up, right? Taller person has less effort to put in to make that hoop than a shorter person, right? Soccer? The goal is on the ground. So, there you go. Right? So if you observe these, there is a difference in there is a difference if I throw this marker on Earth, Mars, Moon, or just chuck it in space, far away from all other objects. Gravity impacts on how fast it's going to start returning to the surface of the Earth, or wherever you are. We throw something up. Note that it first stops and then changes direction to come down. You can't use self-propelled stuff for this, because rocket that is self-propelled is designed to escape to achieve an escape velocity of the planet and never return. Well, Elon Musk returns it. So you throw something up, it stops at its maximum height, comes back down, courtesy of G. What is V0? Note that I'm releasing this marker from the same height all the time. I'm going to give it some initial velocity, but I'm always going to open and let go here. So I can do this. So that was V0, and I can do this. See that? So I release that. So I release this marker from the same Y0 both times, but with a different V0. And this V0 is the one that let the marker go up to here, or almost hit the ceiling and then come back. So these are the three, and that all happens in time. If you want to know and learn physics, the most important thing in all of physics is to have your equations balanced to the point where all of the units across the equation are balanced out. Now, this propagates down to courses and everything that is below physics. You know how it goes. It goes like this. The math sits on top, right? Then you have empty void forever. And then finally there is physics, right? And then that trickles down to all of the engineering and chemistries and all of that kind of stuff. Eventually you get to biology, right? And you know where social justice is? From here, it's in a negative, all right? It's not even on the list. But anyway, so now, when you think about this, your physics, all of it works this way. If you measure your heart in feet, then each one of these terms that you are adding must be feet plus feet plus feet, otherwise you are doomed. You don't get to add 3 elephants to this marker and call it 4 markers or 4 elephants. You add markers and elephants. In Serbia we use grandmas and frogs, obviously, but here you use apples and oranges, so I can use apple and oranges analogy for it. So when you look at the units for gravity, that's going to be feet per second squared times second squared, because time is squared, and when they cancel out, you get your feet. Your velocity is feet per second, miles per hour, meter per second, right? Times a single second for a single t, they cancel, you get your feet, and the y0 is simply the height from the, right, in this case when I release from here it's 3, right? So that's feet altogether, so feet equals feet plus feet for feet. Anytime you write the physics formula down and you're scratching your head, is this good? You can do what we call unit analysis. If that thing works out, most likely you have correct formula. If it doesn't, your formula is 100% wrong. There's no doubt about it. Because it has to be that feet is equal to feet plus feet plus feet in the units realm. So that's a good point to, to keep in mind as you go through any formula. All right, now, if you wrote underneath this formula, I need you to copy this formula again because we're going to do derivatives now. I should have told you that the story on units goes on the side. So my job now is to develop the formula that will calculate velocities. This is the reason why we are able to have engineering. You can come up with a mathematical formula which can calculate speeds and acceleration and all these things, and you can build devices. So my velocity in time is the derivative of the position function. Well, -1/2 g is a constant. We know that we copy constants when we differentiate. So -1/2 g is copied, and the derivative of t squared is 2t. Very good. Derivative of x squared is 2x. Right? So derivative of t squared is 2t. Plus v0 is a constant, derivative of t is 1, and y0 is a constant, derivative of that is 0. So you cancel your negative half and a 2, and what you get is that the velocity in time is equal to negative gt plus v0. Now, if you didn't go, aha, yet, I'm going to ruin it now for you. Velocity final is equal to velocity initial plus acceleration times time. Remember that formula from physics? There it is. That's where it comes from. Now, my acceleration is gravity negative g because it goes down. So, with a being negative g. It's the same formula. These formulas were not arbitrary. They all come from here. Now, finally, for acceleration, a of t is derivative of velocity in time. It's negative g in this case, right? So now you have your 3 equations of motion for parabolic motion, which you seen in your physics class. The units still work, right? Meters per second squared, meters per second squared. This is meters per second. Meter per second squared times second, one of the seconds die, you just meter per second, and then meter per second, great. So it all works out. So these are the equations. And now you can calculate stuff. You can calculate how long will it take the object to hit the floor when you throw it. The other, right? So how many seconds until I hit detected right over there? How do I figure that out? Well, I know the gravity, I know initial velocity, I know the starting velocity, it was almost 6 feet, right? I know that my target is 0 height because it hits the floor, right? So the only unknown variable is t. Hey, use the quadratic equation, right? Use the quadratic equation and you come up with t equals a number. 1.7 seconds, or whatever it is to hit over there. So you can calculate how long, how much of a time, how long in time the object is going to travel for. You can calculate its velocity at all times. If you're interested in how fast that marker is going, in 1 second, you plug 1 over here. You know g, you know v0. And by plugging in t, it will tell you how fast it is moving. Now, this is only the vertical motion. In Calculus 3, we are going to upgrade this and add components. You will do the same thing in physics and a bunch of other classes at the same time. If you're engineering major, you will be learning vectors from scratch and this thing exactly 5 times. So 5 different courses, and one of those is going to be Calculus 3, when you're going to do this 2-dimensional motion and 3-dimensional motion. And obviously physics, and then statics and dynamics, and then a bunch of other courses. Linear algebra, if you take that course, so you will learn and relearn this a few times. So I can calculate the height of the marker at all times. If you are interested in what's happening at 2 seconds, you plug in 2. I can calculate velocity at 2 or 3 or 5 seconds. Acceleration is always this, right? And we can calculate max height. What happens at max height? Well, here's the experiment again. What happens with a marker at the max height? No, but at the max, I'm not touching it at the max height.
Zero acceleration.
Zero, no acceleration, zero speed, velocity. So at max height, we have velocity equal to 0. That is very important because your marker was going one way, stopped, and then went the other way. On some supercars, they have locks on the shifter so that you cannot shift in reverse by accident. Because you can't even imagine what happened, right? You're going 200 miles per hour and shift in reverse by accident. They actually have release handles designed by engineers, and you can't mess up. You cannot shift into reverse while driving forward on your automatic car either, by design. So the velocity is speed plus direction, so the marker is going up. When it reaches maximum height, it stops and then changes the direction going down. So your initial velocity, the one that you get from, what's the difference between dropping something as an oops and slamming it into the the floor? What's the difference?
Sure.
Insurance?
The jerk.
The check?
Oh my god. The jerk that you were talking about when you like go forward or backwards.
Yes, but I was thinking of something else.
There's forward?
So, nope.
No?
Yes, that's the only thing. This puppy over here. That's the only difference between whoops, right? Because you saw what happened when I did oops, right? I just let go. That's it. There's no initial velocity. Initial velocity is 0. This whole term is 0 for dropping things. Now, I don't get to go for maximum height if I'm dropping, right? You've probably seen the little kids try to toss the ball, right? I'm going to try to hit you now the same way with the kid, right? No, there you go. I know. The best part of kids throwing. Have you ever seen? I don't know if you ever. I observed kids dropping things. It's amazing. That's what I would like for me to make baseball interesting. All of the players have to be 2 or younger. That's it. Otherwise, it's boring, and I would rather watch the grass grow. All right? You see a 2-year-old running, you know it's going to fall in the next 10 steps. You're hoping it's going to throw the ball before it falls, right? And it gets there, it's like, okay, perfect. Yes, got it, right? Excellent. So, if you want to have maximum height, the initial velocity cannot be 0, and that's going to be the fastest that object will ever go. Because the moment it leaves your hand, it's going the fastest, and then gravity is slowing it down until it stops at the maximum height with velocity equals 0, and then starts picking up height because acceleration, gravity, is accelerating the object, and the object picks up the speed and goes down. So, it starts with a maximum velocity from your hand, it goes up, and then at the peak of its height, it goes down. If you ever go to any of the tall buildings, never, ever, ever drop anything from the roof. Empire State Building or wherever you go. And they have nets, actually, to catch the stuff because stupid Jimmy is going to go and make a wish. Whee! Tosses a penny. What happens with a penny that's going to fall under gravity from that height? Yeah, it becomes worse than a bullet. If it hits anyone on the way down, that person is gone. They have nets to catch this. Never, ever, ever drop anything off of the top of the building or the bridge or anything like that, Because, you know, it's a little stone, right? And you, like this off of the bridge. If it's a large bridge with a big drop, there's a fisherman underneath, depending on the luck. Yeah. So never ever do that, and you see why. This is your acceleration over here, that your initial velocity, that can be just this, is going to accelerate because of this term and pick up insane speed over time, going down to potentially be very, very dangerous. So these are the three equations. Now, what are the problems? The problem is the position function is blah, blah, blah. What is the velocity function, acceleration function? What's the velocity in 2 seconds? What's the acceleration in 5 seconds? And what, right? So you can get anything because you know how to differentiate. You can get anything as a position function. This was a specific example that used polynomials. You can have anything as a position function. Your job is to differentiate twice to find velocity function and the acceleration function, and then plug in the time to figure out how fast the object is moving or what is the acceleration of the object at that time. So these formulas here hold only for parabolic motion, which is when you throw something which does not propel itself. If you throw something up, it comes down, these equations as well. If you drop something, these equations hold as well. If you toss it across the room, these equations hold as well. This does not hold for rockets or a chicken, as I mentioned, because those are self-propelled. Airplanes and stuff like that. So you have position function s of t given as t squared e to the t, and we are looking for velocity function, acceleration function, velocity at 3 seconds, acceleration at 3 seconds. And that's it. Very simple. So our x is actually t in this problem. So our derivative in respect to t for both velocity and acceleration. So what's my velocity v of t? How do I differentiate this? Product rule, very good. I have a function t squared that's multiplied in a different function e to the t. So we have to use product rule to come up with a velocity function. Copy the first, derivative of the second, plus copy the second times derivative of the first. And for sake of calculation, we factor out t e to the t, and we are left with t plus 2. Do you want to differentiate from here? No, because this is a triple product. You want to differentiate from basic product rules. So we'll find acceleration from this one, but we'll calculate v of 3 here. So now, in blue, to find my acceleration a of t, I will go back to the equation above because I still have to deal with two separate product rules. Again, please look at this. You have a linear function t, you have e to the t, and you have t plus 2. That's a 1, 2, 3 different functions. Now what you can do is you can multiply this t here and then just have one product rule. That's cool. right? Or you can do two product rules on the upper equation. So copy the first derivative of the second plus copy the second derivative of the first plus second product rule, copy the first derivative of the second plus copy the second derivative of the first. So A of t is, I'm going to kick out e to the t. What's left is t squared plus 4t plus 2. Right? Because you have a 2t over here and you have 2t over here. So 2 plus 2 is 4. And it's the middle one, t squared and 2. Good. So I have my functions. I have my velocity function. I have my acceleration function. So now, velocity at 3 seconds is 3 e to the 3 times 5, which is 15e cubed. Meters per second, feet per second, whatever the units are, miles per hour. And acceleration at 3 is going to be e to the 3. This is 9 plus 12 plus 2. That's 23 e cubed. So if my position function was given in meters, then velocity would be given in meters per second, and acceleration would be meters per second squared. If I include units, it's points. If you don't put the units, then the point's off. Units are extremely important. We all know the story of the Marshland, right? Do the engineering in one system, program it in another. You just have to hit the planet. It's good. Some $1 billion, right? Well, it's the marvel of engineering. They'll never make that mistake again. So there's a plus, right? There's that plus there. Say we have our y of t as negative 16.1 t squared plus 3t plus 9. What's the max height? So what should we do? What do we say? What happens at the max height? Great. What is the word you use? Velocity. Is this velocity function? So what's the first thing you have to do? Get the velocity function. Good. Derive it. Let's go. What is your velocity function? So what's the velocity function? Plus 3. Good. So now, to find the max height, what do? You said velocity? Yes. So, equal to 0 at max. From this equation, you will figure out the time at which the object is at the max height, and then you will plug that time in the original equation to figure out the height, because this is your height. Y of t is the height. So we have negative 32.2, t is equal to negative 3, t equals negative 3 divided by negative 32.2, which is roughly what? I'm sorry? Yeah. So we can keep it as 1/10. So about 1/10 of a second. Here, we'll put the squiggly equal. 1/10 of a second. By the way, what are my units? Meters per second or feet per second? Feet per second. Why? Because 32.2. Yes. It's clearly listed right here. If it's 32, then it's feet per second squared. So now I have my time. Time is 1/10. We plug that in original function. So max height, y max, is equal to negative 16.1 times 1/10 squared plus 3 times 1/10 plus 9. This is negative 16.1 over 100 plus 3/10 plus 9. You can make all of this over 100. Negative 16 point, well, it's negative 16. Plus 30 plus 900. So 914 over 100, about 9.14 feet. 9.14 feet would be the maximum height for this object. Again, this is all about, because it's not exactly 1/10, then use the calculator here. So it's all good. So that's that. Now there are some other physics formulas that they present in this section. Since this is not a physics course, I'm not going to bother you with the range and some other things. Do look it up if you're engineering, especially if you're mechanical engineering. You need to know these formulas in your sleep, because the kinematics is the first thing that you learn for your mechanical engineering. Also electrical engineering, important, and so on. And that's the first part of the lecture. The second part of this lecture is going to be on population growth. So I know I mentioned earlier, right? Population of US is declining in terms of newborn babies. For the last 2 years, we are below replacement level, meaning the amount of people dying is bigger than the amount of babies being born. Now, there is a lot of immigration in US, so population still goes up, but the American born, it's going down. Now, we can take a look at the population, either population in a state, population in a country, population in the world, and we can look at and make predictions. Now, what follows is clearly your pre-Calculus 1 problem, where you figure out the rate of growth, and then you come up with a mathematical model. Now, population growth, generally we look at basic y equals a e to the kt. This is standard exponential growth model, k bigger than 0. And we know that this is a very bad model for population on a long run, because the graph for something like this is exponential graph, which allows for population to go to infinity as time grows. Now we know that we can't support infinite amount of people on the planet. It's the finite size. There's a finite surface area with finite amount of land to build housing on and whatever. We don't live very well in deserts and ice caps and oceans. Contrary to what popular movies would say, like Aquaman, fine, but that's just one, all right? So we have finite resources, the amount of minerals, the amount of food that we can grow, whether it's plant or animals. So talking about there is no population crisis, there's no talk about it. Population crisis is there. The question is how good our estimates are on what the carrying capacity of the planet is. And the school of thought goes anywhere from 10 billion to 15 billion people that the planet can sustain. That means mining the resources, growing the food, having the land to build housing on, including buildings and houses and everything else. So there's debate and all of this, right? I don't care. Pick whatever number you want. We are at 7.5. So there is a website that you can go and it's called Population Clock. Which is a .gov website. So you would think they would give at least, $20 to someone to come up with the model that it's ticking right there. So it lists the population of United States and population of the world. And if you take a look at the numbers, the number last year when I taught this class, which happens roughly at the same time in the semester, was 7,423. And now it's 7,559. So we added more than 100 million people to the planet, 100 million to the planet in a year. What we are going to do now in calculus is we're going to come up with the formula, and then we are going to differentiate that formula because the derivative will tell us the rate of change of population per year. So you will be able to calculate how many new people in 2020, how many new people in 2021, 2022, 2023. So each year would be the rate of change, which represents the amount of people added to the population in just that 1 year. That's the power of mathematics. Okay, so that's that. So now let's take a look. The current population in 2019, which is time now, is 7.56 billion. World population in 1989. 5.2 billion. So 1989, 5.2 billion. Now I am going to set 1989 as t equal to 0. That's one of the oldest tricks in the book for math, which makes the year 30 years later, right, makes it into, oh. So I have these 2 points in time. This is data, right? This is data. 2019, 7.56 billion. 30 years ago, 5.2 billion. So this has to be t equals 30. The difference between these two is 30. So now we go and use this information. So we have the point 0, 5.2. Now immediately when time is equal to 0, this is your initial population P0. And we have a second point that is 30 and 7.56. So the population at any time, this is now standard pre-calculus, you should be able to do this in your sleep. We plug in 5.2 e to the kt. Then we plug 7.56 for population, 5.2 e to the 30k, because that's the 30t, right? T is 30. We divide and then take the ln. So you'll need abacus for this one. And when you do your ln calculation, make sure you use 4 decimal places. 4 non-zero decimal places. We call that significant digits. So we have 7.56 divided by 5.2. Which is 1.454 is equal to e to the 30k. We ln both sides. Standard stuff, guys. So ln of 1.454 close parenthesis divided by 30. We get our k equals 0.01248. So I ask you for 4 non-zero decimals. And now I have the population model. It's a lousy one, but it will do. So now, you can go, not too far, but you can go to the past, and you can go a little bit to the future with this model to figure out when you are going to hit whatever you believe is going to be the upper limit of population, called carrying capacity of the planet. If you want to push it all the way to 15 billion, you will plug in 15 over here, and you will figure out the time, which will be 40 years, 45 years, 60 years from today, right, to hit the carrying capacity. Now, that's all pre-calc. What I am interested for this particular problem is to find the derivative of this function, because we want to see the rate of change of population year per year. So, rate of change of population per year is given by dp dt, which is the derivative of population function. Now you copy your 5.2. You know that the derivative of this is you drop the number in front times e to the same number, t, and all you need to do is to multiply these two numbers. So the change in population in time is times 5.2, 0.065 e to the 0.01248 t. Calculates the change of population in time. So now, t equals 0 at 1989. So if you want to know how many people we are going to add to population of Earth next year in 2020, you need to plug in 31 into this equation. So, the number of new people added to the population in 2020 will be, now 2020 means t equals 31 because t0 is at 89. So you will do the dp dt is equal to 0.065 e to the 0.01248 times 31. Now this is a straightforward plug everything in one shot in the calculator. 0.65 times e to the open parenthesis 0.01248 times 31 close 0.0957 billion. That's almost 100 million, right? Which was consistent with what we saw from that clock that was moving about. So about 100 million. I'm just going to say about. These models are not that precise because this is the worst one you can possibly use, right? Logistics models are the ones that you actually want to explore if you want to go into these kinds of things. You're starting with some initial population P0 and then it flattens out at your carrying capacity K. That's called logistic model. You do experience exponential growth in population and then flattens. Because when there is no food, people are competitive, right? For food and the other resources. So that's the population. We have population model, that's all your pre-calc one, and then we differentiate that model to come up with a formula that we are interested in this class, which measures the rate of change of population in time. All right, the last part is going to be the one that I'm lifting directly out of textbook because it's an amazing example. This is business and economics now. What do we know about business? Pretty much all of them fail, right? Why? Because people don't speak numbers. I have a great idea. Oh, great, I ran it into the ground. What do you mean, what was my profit margin? What is the profit margin? Oh, really? Okay, now I got it. So, if you want to be successful in business, you have to understand the game. You have to know what cost is, the cost function, revenue, and then profit. You have to be able to play with these numbers, make good predictions, right? And it really takes mind for that. It's not arbitrary, and it's not luck. Do you think that anything that Elon Musk is doing luck? He's running 10 companies at the same time. You probably know 2, maybe 3, right? If you follow. He's running 10, right? SpaceX and Tesla are probably what most people know. But there are 10 companies. So, what is the thing that he mastered? Right? Does he have formal education in this? No. He read 2 books that were important, and that's it. So, when you are talking money in business, you are talking about profit, revenue, cost most of the time. And all of those are important. So, profit is important because you need to sustain your business. See, cost is what you have to spend to get your product on the market. Now, that includes shipping the product, which means you either own the truck or you rented the truck, or if you have to import that from your factory in China, the import costs and taxes and the cargo ship and insurance and all of that stuff, all of that is cost. If you are making product here in the United States, I understand it's a very foreign thing to say, but if you are making a product here in the United States, there's a cost of labor, right? So what you do is you immediately close the factory and you move it to Mexico, and then it's like 80 cents per hour and so on. If you can move it to Malaysia, wow, that's 7 cents per hour. It's even better, right? So you have a factory. Every machine in that factory is purchased by you. If a machine is $1 million, it goes in a fixed cost. Plastic products are made out of plastic raw material, which you have to buy. And then, because where's plastic coming from? Oil. From oil. Oh, exactly. So, do you think that the company that makes these markers has its own rig and his own refer? No, right? You import, you buy the raw material, you buy steel, you buy aluminum, you buy plastic, and then you make your product. So you have a fixed cost, right? And you have a variable cost. If I'm going to make a truckload of markers, I'm going to order a truckload of plastic. I'm not going to order, right, 7 trucks of plastic to make 1 truck of markers and then, right. So it scales. So cost is the one that it's extremely important. Your salaries for workers, including the gas, electricity, the building, all of the maintenance costs, I don't know, if you have a fish tank in your thing, it's just fish food, everything. Every single thing that is there to run the business is going to be in that cost. So you have a cost, and then you want to see that cost in respect to the product you make in 2 different ways. Cost, an average cost per product made, and then marginal cost, which is the derivative, per product made. And there has to be a certain trend in order for your business to make sense. Usually you know that when you are buying bulk, it's a cheaper price. It holds pretty much everywhere except if you go to Costco. I'm not sure if you noticed that, but you buy bulk, you buy more than if you went to ShopRite and bought 2. So it's all about marketing. So when you produce and mass produce something, the first unit you make is insanely expensive. If I am planning to make 1 billion of these markers and sell each one of these at $1, I'm going to make $1 billion in revenue. But if the machine that makes these markers out of plastic and all the things that you pour into machine costs $2 million, and I make it and I actually managed to make only 1 marker, what's the cost of that marker? It's a $2 million, right? It's a $2 million cost because I had to buy a $2 million machine. I had plans to make 1 billion markers, and then I make $1 billion, and then I give 2 million, right? You see where it goes? Now, the more you make, the cost of that machine is spread across each unit you make. So the more units you make, the lesser the cost per unit. That has to be observed in your equations if you want to have successful product. And another concept that I will explain when we do some calculations. So let me get you started with the problem. This is some kind of manufacturer that makes something. So first I'm going to say that we have a cost function C of x. X are units produced, units made. Then we have the average cost, which is C bar, which is cost function divided by how many units you make. And you have marginal cost, which is simply the derivative of the function. So these are this is the cost function analysis. Now, you take business courses, you will say, okay, the cost function is the variable cost and fixed cost and blah, blah, blah. You go deeper into all of that stuff. Now, what do we have for our problem? Cost function is obtained to be negative 0.02x squared plus 50x plus 100 for the 1,000 units made. Immediately, we can calculate the average cost function, which is each one of these divided by x. So that's negative 0.02x plus 50 plus 100 over x. So you divide your cost function by x. You have the formula on top. There's a formula right there. So that will be our average. And our marginal, C prime of x, very simple, just take the derivative. Negative 0.04x plus 50. So now I have my cost function and cost analysis functions. Part A is asking us to figure out the average cost of the first 100 units made. All right. That's going to be negative 0.02 times 100 plus 50 plus 100 over 100. That's negative 2 plus 50 plus 1, which is $49 per unit. $49 per unit. So I calculated that the average cost of the 100 units I made, I don't know what those 100 units are. It's something, calculators, all right? Do I sell them at 49? Do I sell them at 50? Do I sell them at 60? You see that? You have to be very careful. You have to know your cost because you have to make profit. What do you do with profit? You put it in a bank and you weigh with it? Oh, I have $7 billion in the bank. No. With the profit, you have your R&D, hire engineers that cost money to improve and develop your product so you are relevant on the market. Let me ask you, how many of you are rocking iPhones 1 from 10 years ago, right now? There will be exactly 0 of you, right? Imagine if that dreaded company never invested in any R&D and never came up with a Model 2, 3, 4, 5, 6, 7, right? Would they be relevant today? No. I mean, they're still irrelevant, but in the eyes of those who know. So, the profit is the one that will allow you to further your product. So you must make profit, and you are not allowed to sell this product for 49 or 50 because you're not going to make any profit on it. Next one is the marginal, which is the derivative, and that's negative 0.04 times 100 plus 50, which is negative 4 plus 50, which is $46 per unit. Now, what is this? This is the price of the 100th unit, not the price, sorry, this is the cost of the 100th unit. So the unit, it's not the average of all of them. This is, you know, how you're producing stuff and it's moving on that belt, right? And you go, okay, 96, 97, 98, 99, 9, and 100. All right, you pick up the 100th unit. That one cost you $46 to make. Now, is this an important piece of information? Yes, it is. Because you see that your cost of the 100th unit is smaller than the cost, the average cost. This means the more you are producing, the cost is decreasing, right? If the cost is increasing because of the maintenance of your equipment, that it's breaking every other day. I actually know the plant that shut down in Flemington because they couldn't keep up with the maintenance costs. So the marginal cost skyrocketed over the average cost, and just the whole thing immediately went to hell, right? So these things are very sensitive. So you're looking at the average cost, you say, okay, it cost me roughly $49 to make each. But then you calculate the 100th one, and you say it's 46. Great. That means that the more I produce, the price is going down. Now let me do the same analysis at 900 level. So at 900 level, I have negative 0.02 times 900 plus 50 plus 100 over 900. This is negative 18 plus 50 plus, who cares, 1 over 9. Okay. So this is roughly $32 per unit. Time to do a little dance. Woohoo! Because you compare the 32 to 49, right? We're doing great. because I just produced extra 800 units and the cost per unit is going down. Excellent. I have a very profitable future with this model here because it shows that I am able to produce, as I am scaling my production up, the cost of producing everything is going down. You can go and research Elon Musk gradually increasing the production line. Yeah, customers are angry they had to wait additional 2 years, but he is not stupid, right? Line by line. C prime, 900, negative 0.04 times 900 plus 50. This is negative 36 plus 50 equals to $14 per unit. Oh. Nice. The 900th unit, right? So you're looking at these things are going on, right? So there's 898, 899, 900. This one, right? You pick that one off of and that one cost you $14 to make. So now you see very healthy drop in cost as you're producing more and more of these. Go ahead, calculate for 1,000. Now the model only holds from 0 to 1,000. Why? Because there is a time frame in which you have to produce your stuff. So probably 0 to 1,000, and then I have to buy another machine, right? So, now my cost is different, right? Because I just spent another $2 million to make it. By the way, the medications that you take from the doctor, they all come from this huge, my friend told me, who actually worked on these machines. The companies that make medications and sell them have this huge, I can't remember the name of it, but Sanofi had 4 of them. Each one of those stainless steel, cylinder-shaped, 4 stories tall machines is $1 billion. They put that thing in, and then they build the building around it with levels where the workers can access to add ingredients on what type of medication you are making. So it's one machine that makes them all. It's just what you put in it and on which level and in which way it goes through the systems that are inside. 1 billion fixed cost, which is nothing for pharmaceutical companies. That's like a write-off check for one afternoon. Sanofi had 26 buildings. 26 buildings in Bridgeport, right? 26 buildings. Needed air conditioning. Research, development, everything was there, right? So when you consider the cost, there is a time frame in which you have to deliver these units. So if you now think, oh, let me see what happens if I plug in 5,000, you are going to get bad numbers. Because the model clearly told you that this is up to 1,000 units. Why? Let's say you are making allergy medication for seasonal pollen stuff. How much of that do you sell in November? 0, right? How much of that stuff do you sell in March or April? About 7 trucks of it, right? To one person. So, who needs them, right? So, there is a time-sensitive delivery for certain, let's say, medication. Do you know game console? Whee! Right? What happened when it came out? People waited 6 months to buy it because the company didn't anticipate how popular it's going to be. They made a number of units, shipped them to the market, and then everyone was screaming for months. More, right? So when you have the business, you need to also know supply and demand and all these kind of things. So you take your business courses and figure those things out. But this kind of calculation helps you to figure out if your business is actually sustainable, right? Because if these numbers from 100 to 900, if these numbers go up, your cost is going up as you're making more units. So something is terribly wrong. And you are going to fail because your cost needs to reduce and go down as you are either scaling to make it bigger, or to make more of your product, or to, so if you don't understand the derivative, if you don't understand how this average versus derivative works and what it tells you, right, you are pretty much guaranteed to fail. Or you have to pay someone who does understand these types of calculations and projections so that your business on the long run is profitable. Still want to be in business? That's good. That's good. And that's it. That's the rates of change. We learned that there is that the rate of change is measuring the change in time. We did velocity, acceleration. They were all changes in time. Change of velocity in time for acceleration, change of position in time for velocity. We learned about change of population in time, right? Population either increases or decreases in time. And in the end, we take a look at, now this change over here was change of cost, not in time, change of cost per unit produced. The more I produce, I want to see the cost per unit going down, because that will allow me to make profit and then invest that profit into research and development. Or you can do what Apple does, right? You go, you see something you like, you go, you buy it, and they say, we invented this, hey! Right? Or even worse, Samsung puts out the curved screen. Apple says, ooh, that's cool. And then they go like, you know, the little ones they are, can we have that? And the Samsung says, yeah, you're nothing for us. So here you go. And then the next year, Apple has the curved screen, and they go on the stage, we invented this. And I'm like, yeah, did you take a look at the last year's product line for Samsung? They actually had that curved screen. The audacity of that company is unbelievable. It is unbelievable. The things they would say just to market their crap products at the prices that are just, If you want to see, like, in one company that is the most immoral probably on the planet, just look at Apple all the time. You will never get disappointed. It is unbelievable what they do. God, I hate them so much. Like, all right, that's it for this one. Let's see what's next.